the last class we've been doing some examples on algebraic extensions, and in this session also we are continue doing some more examples and problems. We are going to start with a finite extension and see what will happen if there is an integral domain in between this base field and the extension. So let E be a finite extension of F, and we are going to consider a D in between these two fields, and D be an integral domain such that F is contained in D, which is contained in E. Now, our problem is, what can you say about this D? Can it be a field? It is only an integral domain as of now. So what we are going to do is, we are going to take the property of finite extension. So E is a finite extension of F implies E is algebraic over F. We will take an element from D, is not equal to 0, belongs to D. That means alpha belongs to E. That means alpha is algebraic over F. So let us assume that F alpha, the degree of alpha over F be n for some n. That means F alpha is equal to A0 plus A1 alpha plus dash dash an minus 1 alpha to the power of n minus 1, then AI belongs to F, for AI belongs to F. But F alpha is a field. F alpha is a field means F alpha is a field and alpha is different from 0, implies 1 by alpha belongs to F of alpha. So since every element of F of alpha can be written as a linear combination of alphas, 1 by alpha can be written as B0 plus B1 alpha plus dash dash B n minus 1 alpha to the power of n minus 1 for some Bi's in F. So Bi's are all in F and alpha is in D. So Bi's are in F, which is contained in D, and alpha belongs to D, implies 1 by alpha belongs to D. Because it's an integral domain and we are taking a linear combination of multiples of elements from D. So definitely it is closed under addition and multiplication. So what did we do? We took an element, a non-zero element from D, and proved that its inverse is also in D. So what is the difference between an integral domain and a field? In an integral domain, if every element has a multiplicative inverse, that will become a field. So this implies D is a field. Let us do another problem. So let E be a finite extension of F, and P of X be an irreducible polynomial in f of x such that the degree of p of x does not divide, write it as does not divide the degree of E over F. Meaning the degree of P of X is not a factor of the degree of E over F. Then the question is, can we have a zero of P of X in E? So it is actually like this: E, F, and there is a P of X here which is irreducible over F. Then the question is whether we can have an alpha somewhere here so that P of alpha is equal to 0. So let us assume that alpha belongs to E be a 0 of f of x, sorry, P of x. And let the degree of P of x as a polynomial be m. And we are also going to assume that let E over F is equal to m. What is it given? What is that it is given? M does not divide n. So since alpha is a 0 of P of x and P of x is an irreducible polynomial, what can you say about f of alpha over f? This is actually now, this vector space is generated by m elements because P of x is a irreducible polynomial. Okay, or we can also, one more step, we can write it like this in order to eliminate the confusion. Degree of alpha over f is equal to m, because m is a degree of the irreducible polynomial for which alpha is a 0. So this implies the degree of f of alpha over f is equal to m. But we know that f is contained in f of alpha, which is contained in E. Everything is a finite extension. And that means E over f is equal to E over f of alpha times f of alpha colon f. This is our n and this is our m. And we already assumed that m does not divide n. So this is not possible. This is not possible because m does not divide n. That is what we assumed. So why we arrived at this contradiction? Because alpha is a 0 of p of x. So that means p of x does not contain a 0 in E. We'll do one more problem. Let E be a finite extension of f and alpha belongs to E be algebraic over f of degree of an odd degree. Then what can you say about the degree of alpha square? See, alpha is algebraic over f of odd degree. So if it is 1, our question is what is the degree of alpha square? Can it be odd or even? That is the question. If the degree of alpha over f is equal to 1, that means alpha belongs to f, that means alpha square belongs to f, that means degree of alpha square over f is equal to 1. No problem. So this is also odd. The degree of alpha square is also odd. No problem. This is a trivial situation. I want to eliminate trivial situation before coming to the main argument. So let us assume that degree of alpha comma f is greater than 1. Okay? So this implies that f is contained in f of alpha, which is contained in f of alpha square, which is contained in f of alpha, which is contained in E. Because this is our f, this is E, and it is actually outside here because we already eliminated the situation where alpha is inside f. So it is somewhere here. So alpha square is inside this f of alpha. Alpha square is inside f of alpha. So definitely the smallest field containing alpha square and f is contained in here. So that is what this means. So from here we can write it as the degree of f of alpha over f is equal to f of alpha over f of alpha square times f of alpha square over f. We know that this is odd. That means both these numbers are to be odd. Right? So that implies f of alpha square over f is an odd number. And that means alpha square or degree of alpha square over f is odd. So if alpha is algebraic with an odd degree, then alpha square is also algebraic over f of odd degree. We are going to do another problem. Let's take our base field as the field of rational numbers Q. And of course, R is an extension of Q. So, and you take two elements Q such that root A comma root B are algebraic over Q. Then the question is going to define two extensions of Q. One is Q of root A comma root B. Another one is Q of root A plus root B. Question is there any relation between these two? Of course there is a relation. That is obvious relation is R Q root A root B, and this is our Q of root A comma root B, because that is the field containing both root A and B, smallest one. And of course root A plus B resides inside this. So definitely this extension is contained in here, because this is the smallest extension containing root A plus root B, and definitely this has that element. So clearly Q of root A plus root B is contained in Q of root A comma root B. Now there are two situations. Either it can A equal to B or A not equal to B. We want to find out whether the other inclusion is possible. So when A is equal to B, then this will become q of root a comma root a, and this will become q of root a plus root a. So this is actually q root a, because this is same. This contains q root a, and this contains 2 root a, and that is q root a. So when a is equal to b, that means q of root a comma root b is equal to q of root a plus root b. Now, when a is not equal to b, we want to find out whether the other inclusion is possible. So, if you can find that in this extension it has got root a and root b, then we are done. This is more granular. If this has root a and root b, then that is the smallest field containing root a and root b. So our idea is to find whether root a belongs to this or root b belongs to this. For that, what we do is, so root a plus root b belongs to q of root a plus b. Sure, no problem. And this is a field that implies the multiplicative inverse also belongs to q of root a plus root b. Right? So what we do is, this is actually implies, what we do is we multiply root a plus root b times root a minus root b by root a minus root b. Doesn't matter this is inside or outside of q of root a plus root b, because this element exists and we are multiplying with an identity. So this actually equals root a minus root b by, this is a minus b. Right? So we are assuming that this is different from b, a is different from b, so this cannot be 0. So this is actually equal to root a by a minus b minus root b minus a minus b. Right? So what I'm going to do is, so this actually belongs to q of root a plus root b. So what we are going to do is, that means root a by a minus b minus root b minus a minus b plus, this is an element from q of root a plus root b, and this is also an element from, so what we are doing, root a plus root b by root a minus b by a minus b. This also belongs to q of root a plus root b, because this is actually root a plus root b minus whole divided by a minus b. So this also belongs to q of root a plus root b. This is an element from root a from root b. This also is an element from q of root a plus root b. And this is equal to, that implies you will cancel this out, root a by a minus b belongs to, actually 2 times, belongs to q of root a plus root b. See, this is an integer or a rational number, and this is a rational number. So this, the whole thing is a rational number. So this rational number multiplied another rational number belongs to this. So this has to be, this has to belong to this. This implies root a belongs to q of root a plus root b. Similarly, root b also belongs to q of root a plus root b. So that means q of root a comma root b is equal to q of root a plus root b. We will do one more problem. Let us assume that there are 3 fields here. Let k is an extension of E, which is an extension of F. And k is algebraic over E, and E is algebraic over F. Then our question is whether k is algebraic over F. So to show that k is algebraic over F, what we need to do is every element of k is algebraic over F. So we'll take an element from k and show that it's algebraic over F. So let alpha belongs to k, be any element in k. So this means alpha is algebraic or E, because k is algebraic over E, and that implies there exists a polynomial. I'm going to write there exists a polynomial p of x in E of x of degree n such that p of alpha is equal to 0 for some n. So what we are going to assume that let p of x equal to a0 plus a1x plus dash dash a n minus 1 x of n minus 1. So this is a polynomial of degree n. So let us take this as n, no problem. X to the power of n, where a0, ai's belongs to E, not F. If this would have been F, then we are done. But E is algebraic or F, and that implies AI's are algebraic over F. And what does that mean? That implies F of alpha 1 dash dash alpha n, sorry. That implies F of a0 comma a1 dash dash an is a finite extension of F. Because they are all algebraic, so this has to be a finite extension of this. We already found that. So that implies we are going to include one more. So F of a0 comma a1 dash dash an comma alpha, adding alpha, an extension, a finite extension of F. Finite extension of F. And this implies alpha is algebraic over F. And that means K is algebraic over F. Now we assumed that E is algebraic over F, K is algebraic over F, then we proved that K is algebraic over F. Now we'll assume that K is algebraic over F. This is algebraic over F. Then can we say that this and this are algebraic? Let us see. K is algebraic of F. That clearly implies K is algebraic over E. Why? Because every element of K is algebraic over F. That means there exists a polynomial in F that has that element as 0. So every element of f of x is every element of E of x. That is because f of x is contained in E of x. That is the reason. Now we all need to prove is E is an extension of algebraic extension of F. So every element in E is an element of K implies every element in E has a irreducible polynomial in f of x that has this element as 0. See, what I'm trying to say here, this is our K, this is our E, and this is our F. We want to prove that E is an algebraic extension of F. So we'll take an element here. What is given? K is an extension of F. We want to prove E is an algebraic extension of F. K is an algebraic extension. If K is an algebraic extension of F, E is an algebraic extension of F. So if you take an element alpha here, this also belongs to K. Because K is algebraic over F, there exists a polynomial in f of x that has alpha as 0, meaning alpha is algebraic over f. And that's what this is. So this implies E is algebraic over f. So the result is, if f is contained in E, which is contained in K, then A is algebraic over E and E is algebraic over F if and only if K is algebraic over F. Meaning this is algebraic over E, this is algebraic over F if and only if this is algebraic over F.